All right, this is Honors Algebra 2 Pre-Calculus, and we're starting 4.3, which is the inverse of a matrix. So one of the cool applications that we're going to learn in this section is encoding messages using matrices. And we'll do a little bit at the end of this section, sort of optional, not necessarily entirely math related, about some other historical encoding methods, the Caesar cipher, the Vigenère cipher. So just some cool stuff at the end. So here there's a table. It's an alphanumeric code, right? A is 1, B is 2, C is 3, and that's pretty standard. So what we're going to learn to do when we get to the later examples in this section is use a matrix to encode a message. Like here, you'll see there's the message help me, right? So the message help me could be encoded with 8 for H, right? So here's H and there's 8, and E for 5, right? And or 5 for E rather, and 12 for L, and 16 for P, and 0 for the space, and 13 for M, and 5 for E again. The trick is that if you just encoded a message like that, if you just rewrote it as those numbers, pretty much anybody that knew it was a message in English would pretty quickly pick up on the fact that they were the most logical method of encoding stuff. So, and if you read this little intro, they'll talk about the Navajo code talkers, because again, essentially during World War II, the United States used Navajo as a language for sending messages because it was not a standard form of encryption, and other countries weren't necessarily able to discern what was happening. But we're gonna move forward with talking about the inverse of a matrix, and we'll do some cool stuff with encoding and decoding towards the end of this section. So moving forward. All right, so a square matrix is a matrix that has the same number of rows as it does columns, like 2 by 2 or 3 by 3, etc. Right? So all this stuff that you see over here, like 2 by 2 or 3 by 3 or 4 by 4. So pretty much what you'd expect a square matrix to be. So the identity matrix for multiplication, right? And usually that identity matrix is written just as an I, right? So an I, either I 2 by 2, I 3 by 3, I 4 by 4, whatever. There could be as many I's as there are square matrices. You could have an I that's 1,000,000 by 1,000,000, right? Basically, what the identity matrix for multiplication looks like is it looks like ones along this diagonal, which is called the main diagonal, and you'll see that right here. That's called the main diagonal, and zeros everywhere else. Okay, so the diagonal from the top left to the bottom right is called the main diagonal. Those are all ones. Everything else is a 0. So let A be a square matrix with n rows and n columns, and I is the identity matrix with the same dimensions. So if you multiply A times I or I times A, you get A. Right? It's like multiplying a matrix by 1, essentially. It doesn't change it at all. So that's going to matter moving forward because we're going to talk about inverses next. So the product of a real number and its multiplicative inverse is 1, right? The product of a square matrix and its inverse is the identity matrix. So if you take a matrix A, so here's A, 3, 1, 2, 1, and you multiply it by the inverse of A, which we're going to denote as A inverse in a minute, and you'll see that down here. If you multiply those two, you will get the identity matrix out. Now, an important note here is that A inverse does not mean 1 over A. So if you think back to where we talked about, remember when we talked about F inverse of X, right? In section probably, 3 point, it's hard to remember. Anyway, regardless of what section we talked about it in, this means the inverse of the function f of x. It does not mean the same thing as if you put an f of x and put that whole thing to the negative first power, which would mean 1 over f of x, okay? So this is the same idea. This A inverse is not a 1 over A. There is no matrix division. You can only multiply in matrices. You cannot divide. Basically, to show that two matrices are inverses of one another, if A and B are inverses, then their product is the identity matrix, okay? So we're going to go ahead and start by showing that A and B are inverses of one another, okay? So to do that, right, I'm going to show that AB, right, I'm going to show that AB, which would be 2, 3, 3, 5, that's A, times B, which is 5, negative 3, negative 3, 2, right? I'm trying to show that this is I. So I definitely have a 2 by 2 matrix times another 2 by 2 matrix, which means it's okay to multiply, and the result is a 2 by 2 matrix. So when I do the work to show this answer, I have my work matrix, and I'm able to kind of skip ahead and know that the answer is probably the identity matrix because they said show. They didn't say are they specifically said go ahead and show that they are. So to get this first spot, I'm going to do row 1 times column 1. 2 times 5 gives me a 10. 3 times the negative 3 gives me a negative 9. 10 minus 9 is a 1, right? To get the next spot, I'm going to do row 1, column 2. Well, that's 2 times negative 3, which is a negative 6. 3 times 2, which is a positive 6. Oh, look, that's a 0. How convenient. To get the next spot, I'm going to do second row, first column. So that's 3 times 5, which is a 15. 5 times negative 3, which is a negative 15, and there's that convenient 0, right? And then for the last one, 3 and 5 and negative 3, 2. Well, that's going to be a negative 9, right? Negative 3 times 3. And a positive 10, because that's 5 times 2, which is a 1. And sure enough, that's the identity matrix. Now, in order to show that they are inverses, I should do both directions of the multiplication. This is not a thing that I'm going to make you do on an exam, because I get that it's tedious and frustrating. But just to show you, if they are inverses, then if you multiply in both directions, you should get the identity matrix, right? So A times B should be the same as B times A, and you should get the identity matrix. So if I do that work again, it's going to become pretty apparent pretty quickly that that's what's happening. So let's go ahead and use colors again. So row 1, column 1, 5 times 2 is 10. Negative 3 times 3 is a negative 9. There's my 1, right? Row 1, column 2, 5 times 3 is a 15. Negative 3 times 5 is a negative 15, so that's a 0. Row 2, column 1, negative 3 times 2 is a negative 6. 3 times 2 is a 6. There's my 0. And last but not least, row 2, column 2, negative 3 times 3 is a negative 9. 2 times 5 is a 10. So there's my 1. And sure enough, that's the identity matrix. So they are inverses. So we're going to do a P1 where you do the same thing. If your brain is like, cool, Hogan, I get it, and I'm over this, that's your choice. That's okay. We're going to walk through it anyway. Same idea, we're going to show that they're inverses. Remember, if I tell you to show that something's true, it's definitely true. So I'm going to go ahead and call this one A and this one B just for the sake of notation. So AB is going to be 2, 1, 1, 1, and 1, negative 1, negative 1, 2. And when I go to do BA in a minute, because I'm going to do both of them, 1, negative 1, negative 1, 2, 2, 1, 1, 1. Okay, so it's definitely not cheating if you're able to do matrix multiplication in your head, like some of this, and I know I'm probably showing more work than some people need, and maybe I'm showing less work than some other people need. So you need to find that sort of sweet spot where you get the amount of work that you need, but remember that these are things that your calculator can do, so when you're doing a problem that your calculator can do, you need to make sure that you're showing me you know how to do it by hand. So 2 times 1 is 2. 1 times negative 1 is negative 1, so there's my 1, my 2, 1, and my negative 1, 2. Well, that's going to be a negative 2 plus a 2, so there's my 0. Bottom row is a 1, 1, and a 1, negative 1, so 1 times 1 is 1, 1 times negative 1 is negative 1, and there's my 0. Bottom row, second column, should be a negative 1 and a plus 2, right, because 1 times negative 1 and 1 times 2. And that's my 1, so that's definitely the identity matrix, check, right? Let's do the same thing on the bottom. First row, first column should be a 2 and a negative 1, which is a 1. First row, second column should be 1 times 1, which is 1. Negative 1 times 1, which is negative 1, so that's a 0, right? Second row, first column should be negative 1 times 2, which is negative 2, and 2 times 1, which is 2, so there's my 0. And then last but not least, second row, second column should be a negative 1 plus a 2, which is my 1. And sure enough, those are both the identity matrix. So yay. All right, cool. Moving on. So we're going to learn a simple formula to calculate the inverse of a 2 by 2 matrix by hand. You are going to have to do that for me with work on an assessment. But for any matrix larger than 2 by 2, you should realistically use your calculator. So if you want to find the inverse of some matrix A, right, so here in this particular example, you're putting this in your calculator as A, and we're going to walk through that right now, okay? So if you wanted to do that, right, what you would do is you would put into your calculator, you go to second matrix, right, and I'm going to have to go over to edit, and now I'm going to want my A to be 2 by 2. It wasn't because I was doing other math before this, right? I'm going to put in 1, 2, 3, and 5, right? I double check that that's right, and then I quit out by doing second mode. Now what I'm going to want to do is I'm going to do A and then the inverse key. So I go back. Now I can't use the letter A. I have to use matrix A. So I go back to matrix, I pick A from the name list, and then I do that -1 button. Notice that it's not an accident that the -1 button is where matrix is on your calculator, right? It's the second and then the X inverse button. That's not an accident. Your calculator is fairly well designed to have the buttons have a relationship of some kind. It's not an accident that square and square root are together. It's not an accident that natural log is with e to the x, which we'll talk about when we get to logarithms. It makes sense the way that your calculator is designed in most cases. So I do that, I hit enter, and then sure enough, there's my inverse. So when you go to find the inverse of like a 3 by 3 matrix, it is much more difficult. So 2 by 2 is very reasonable by hand. But if you try to find the inverse of a 3 by 3 matrix, please trust me when I say that it's not going to be a thing that you want to do by hand unless you are absolutely forced to do it. So we're not going to focus on that, but we're going to kind of keep moving from here. So cool. So we're going to use a calculator to find the inverse of each one of these, right? So you're specifically told to use a calculator. Even though there's some 2 by 2s, we're going to walk through with a calculator. So I'm going to go to my second and matrix, right? I'm going to go over to edit. And in matrix A, I'm just going to edit what's in here. So 6, 8, 5, 7, right? So 6, 8, 5, 7, I double check that it's right. I quit out. And then here's the honest answer. I already did A inverse. If I just hit enter, it's going to do it again. So I'm just going to go ahead and take a screenshot because I'm a lazy human. And there's our A inverse, right? So A inverse equals, that's the first one, right? Now, I know that this other one actually says B and this one says C, but I'm going to be honest and say that that's just because that's what they called them doesn't mean that's what you have to enter into your calculator, right? So if I want, I can go to second matrix and I can just keep changing A. Like there's no reason I have to use matrix B, right? I do have to call it B inverse when I write it down on my paper, but what I choose to enter into my calculator is my business, so why not just go ahead and use the same matrix I was already using, right? 3, 4, -2. Now, the exception to that is when you need to use 2 matrices, then you're going to have to use them anyway, so might as well make sure they're right. So let's double check. 2, -1, 1, -1, 3, 4, -2, 1, 0, right? I quit out, and then I can just hit enter because I already have A inverse. Now, I know that this is B inverse, but again, there's nothing wrong with me writing it as B inverse, right? And again, I'm being kind of lazy and just, writing. So there's nothing wrong with me writing B inverse equals, right? Now, if you would prefer that as fractions, there's definitely nothing wrong with that. A lot of us prefer fractions. You can hit math frac. I said mactions and didn't mean it. If you hit math frac, it's going to give you this answer. Now, whether it looks like that or whether it looks, so right now I think I'm in the math print version, right? Not classic. If you're in classic, it's going to look a little bit different. If you are in, if you're in mode, and I'm usually in classic, but I switched to math print for something the other day. So if you're in classic, go to, oh, that's a while back. Let's do matrix A inverse. There you go. Okay, if you hit math frac in classic, it's going to look a little bit different, right? So that ... just, you can scroll over if that happens, right? So the reason that there's a ... is because it's too wide for the window. So just to show you, that's another option, right? So really what mode you're in, so if you are in classic, it's going to look like this. Any of those are the same, right? And you could have also math fracked this, right? You could have made this 7 halves, -4, -5 halves, and 3, right? That's the same answer. So let's do C. And a thing's going to happen when we do C. So let's go to second matrix. Again, I'm just going to go ahead and put it in A. I don't see a big reason not to. So I'm going to make it 2 by 2. I'm going to make it 8, 4, 6, and 3. All right. All right, and I'm going to go ahead and hit second matrix. I'm going to pick A and do inverse, right? And a thing's going to happen. I'm going to get this error, which I'm intentionally going to put on here. That's not the final answer, right? But I want to point that that's what you're seeing, okay? So what's happening here is that C inverse does not exist. C is what we call a singular matrix. It does not have an inverse, so has no inverse. And that's a thing that can happen. There are matrices that have no inverse. So C inverse does not exist. My reason is that it's a singular matrix, and that's the whole answer. So you're going to go ahead and try a P2, same idea, right? Same idea, give it a try. You're going to do it in a calculator. You don't have to do it by hand. So go ahead, pause me if you don't want me to do it without you, right? Okay, so hang on, we ended up slightly off from where I wanted us. There we go, slightly better. All right, cool. So if we go to matrix, sorry, clearing that out. Okay, so second matrix, I'm going to go to edit, I pick A, I want it to be 2 by 2, -3, 2, 9, -6. Okay, I quit out. Matrix, I want A inverse, and I hit enter, and notice I get that error singular matrix, right? So I'm not actually going to screenshot it. I'm just going to drag the one I had from before in, right? So A inverse does not exist. A is a singular matrix, which just is a fancy way to say has no inverse, okay? Let's go ahead and find B and C. All right, so when you go ahead and put stuff in your calculator for B and C, right, so we're going to quit out of here. Second matrix, edit. Okay, if you want to be kind of lazy, you could do C first because C is 2 by 2. So I'm going to be a little bit lazy since I already have a 2 by 2 matrix and just do C first. Sometimes there are situations where it's just easier to take the short route. So I'm going to quit out, right, and I'm going to hit enter, and there's my answer for C inverse, right? So 4, -5, -7, 9. So my C inverse is 4, -5, 7, -7, 9. Okay, so that's my C inverse, and that's it. I'm just typing it in my calculator. So now I'll do B. The only reason I didn't do B first was because B was 3 by 3 and I was lazy. So second matrix, I'm going to go ahead and edit matrix A to be a 3 by 3. And I'm going to use this 1, 6, 2, -2, 3, 4, 5 rather, 7, 12, and -4. And then we double check that everything's right because that's a big reason you end up surly if things aren't right, and you quit and then hit enter. And it says also a singular matrix. So we're going to also be running into one of, oh, not the right one. Sorry, my bad. This one. Okay, so B inverse does not exist. B is a singular matrix, right? And that just means does not have an inverse, okay? Cool. So there we go. We're going to go ahead and talk about determinants. So, okay, so each square matrix can be assigned a real number called the determinant of the matrix. The determinant of a 2 by 2 matrix is defined below. So let's say you have a 2 by 2 matrix with entries A, B, C, D. The determinant, which is denoted one of two ways, either det A, with the capital A being the matrix, or with the sort of like absolute value symbols, these long straight lines next to A, B, C, D, right, is defined as AD, so it's AD, right, minus BC, okay, AD minus BC. A matrix has an inverse if and only if determinant A is not equal to 0. So the issue that we found there, so for instance, in all those matrices that we called singular, right, so in a singular matrix, the determinant is 0. Okay, that's the issue in a singular matrix, is that the determinant is 0. Cool. So what we're going to do is we're now going to learn how to find the inverse of a 2 by 2 matrix by hand. All right, so this is actually example 4 in your textbook, but we're going to find the determinant of each matrix and tell whether it has an inverse. That's all we're going to do. We're not actually going to find the inverse yet. So the determinant of G is AD, so 49, minus BC, which would be 48. So the determinant is 1. Yes, it has an inverse. Okay, and we don't have to find G inverse. They just wanted us to say if it has an inverse. The determinant of H is going to be AD, which would be 2, minus BC, which would also be 2, which is 0. So no, it does not have an inverse. Okay? All right, so last thing we're going to do before we end this video is you're going to do the same thing in P3. So the determinant of S is going to be AD, which would be negative 27. Sorry, I wrote over it well enough that I then couldn't see. So AD, which is negative 27, minus BC, which is a negative 8. So that ends up being a negative 19, okay? So yes, it has an inverse, okay? And the determinant of T is AD, which is 24, minus BC, which is also 24, which is 0, so no inverse, right? And that, I think, is the end of our video for now. So we'll stop there and pick up